Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
This is Chris Jackson, and Fred is talking about something we all like talking about, and that is software not working.
It's working just fine. How do we know it's working just fine? And I've seen this. I was in a discussion with Carl, and it was completely unrelated to the calculations and modeling work that software does. But the concept came up to me is in recalling a client that was in the medical industry, and they said, "Well, we don't use Excel because then we have to go through all these hoops to show that the Excel spreadsheet that we created is valid, that the information we put into it gives us a true result out of the end of it." And so they use like Minitab, which the FDA says, yep, Minitab's good. And I made the point to him is like, well, if you put absolute garbage numbers in, it will give you a number out, right? And just because the software does addition correctly doesn't mean that it's adding the right things. That's just one issue. But more importantly is that, yeah, Minitab and SAS and all these other software packages do a bunch of work to make sure that they're adding when they should be adding and multiplying when they should be multiplying. Yet I've also know that if you take Weibull++ and Item Software and Relics and a handful of the other packages, I don't think Relics is around anymore, take a whole pile of these different packages and run the exact same data in it, you'll get similar but different answers. Mm-hmm. And so the real question to me is how do you know, or what's the process? And I know that you do a bunch of programming and create app, custom stuff in I think it's MATLAB, I think you use.
Yeah.
Understanding that if you tell it to do addition, it's probably going to do the addition correctly. Mm-hmm. Not trying to validate that it can do what you tell it to do correctly. So how do you know that you're putting in the right commands so that you get a true result versus a random result?
Yeah, well, I mean, there's a lot to unpack there. If you're talking about why Weibull++ and other software packages differ, there's a reason why they differ, and that's because there's about 3 or 4 assumptions that need to be made to get the sort of borderline instantaneous results from a Weibull plot. And when I say instantaneous, something that's repeatable, doesn't need human interaction to oversee the process, as in you will get, for example, a line of best fit, and you will get confidence bounds using these 5 assumptions. It's sort of the actual mathematics becomes robust when you make these assumptions. It's always going to work per se, mm-hmm. but the effects of these assumptions are not well studied, I would argue. In fact, I think one of my webinars was, involved the confidence that you can get, and I sort of showed the gold standard approach and how, off-the-shelf software packages can often have nonsensical confidence bounds, especially when you have small data sets.
You had one where it was folding back over itself.
Right, yeah, and which will always happen. If you look on, let's pick on Weibull++, they'll actually have on their website that you need to be careful for this phenomenon. You need to get more information, get more data. So it's a thing, but they don't really explain why it's a thing, and they don't really go into details why it's. Anyway, it's just still sort of there to say.
Well, that brings up a whole other thing. Is the software packages often, they don't know what kind of data I'm looking at and how to do it. They rarely flag your analysis to say, if this doesn't seem to be fitting this approach, but the software also doesn't know if I'm doing recurrent readings or degradation data and I'm sticking it into a Weibull plot. And mm-hmm. It's just numbers. And I think that's the core problem is that if we don't, and I quoted you when I was talking to Carl, is like, well, you can't check your brain at the door. Like, you got to think through this. You got to do the critical thinking. But that leaves me with, I know I've developed just a healthy, not distrust, skepticism am I doing this correctly? Do I have it right? But like Weibull++ doesn't give you residual plots. And like that's a fundamental thing in regression analysis. We were talking about it in the last episode. If the variance isn't consistent, that the accelerated test model we were talking about there is probably indicating there's something amiss here. And you need to know that. Whereas Weibull++, in their accelerated test cycles, or not Weibull++, it's Alta, I think is their software package. It can do multi-stress modeling and does the regression analysis, but it doesn't tell you that, hey, look, the variances are really different in these things. They have the data. They know that they've calculated the variances. They probably have the residuals or can create them, but it's just, why not flag that? Help the analyst understand that there's something wrong here. And that bothers me. So it's incumbent on the analyst to actually ask those questions and pursue those things. And
I think
that's the idea.
Yeah, I think you just touched on a key point, though. The analyst is also the customer. And customers want software to give them the answer, unfortunately, far too often in our industry.
Yeah. I just want a answer, not necessarily the right answer. Or if my old boss would say, I want the answer that I want, not the answer you're getting. Go back and try it again. Tongue in cheek, I think.
Yeah, they just want a defendable answer. Where'd that answer come from? Oh, it came from Weibull++, so it's good.
Okay, it's fine.
Yeah. So I think that's, it's free market, baby. That's what capitalists want. The customer's always right. They tell you what they want. I just want to put numbers in. I don't want to have to get a PhD to understand how this thing works. Of course, there's a happy medium involved where you really understand what's going on, and that's not as hard as you think. But I think you can break this challenge down into two. I think I've heard two different areas. One is, what is the validity of the data that you're feeding into said software package? And two, what is the process through which you can get some sort of software assurance? I know that for the data itself, one thing I do is, before I even think about analyzing it, I predict what I'd expect to see. It's not down to
6 decimal points or anything.
Right.
But I mean, common things like if we're doing a time to failure or a median time to failure, it should be a positive number.
That's right. Well, I mean, you know how fixated I am in ball bearings the last little period of time.
Yeah.
But you know how ball bearings, the time to failure of ball bearings should be distributed.
Right.
If all of a sudden the distribution for the data you have got is allegedly ball bearings, but it has...
It's bimodal.
You do a histogram plot, and there's clearly two modes. So you've got sort of two mountains of... You go, okay, there's something going on here. You've either got two different bearings in here, or you've got the same bearings, but two different subpopulations being used in completely different scenarios.
Right.
And so that's the sort of interrogation that I like going through at the very start.
Just plot it. We've talked about that so many times. Just get your data, plot it. Let it talk to you. Plot it, do a histogram, do a linear plot, plot it 4 or 5 different ways and take a look at it. Get your eyes busy in thinking about your data. Why does it look like it does? It's not the end of the analysis, but it's kind of, wait a second, why is this one, 3 decades different than anything else? Well, it's either very informative or it's a clerical error. Let's figure it out.
I always emphasize, at least when I'm in my conversations, how predict what you want to see.
Yep.
Because if you plot it the way you can, and I mean, the way you describe, I should say, human beings are wonderful at convincing themselves that they can see what they want to see in stuff, especially if you have no preconceived ideas. If you see a bimodal time to failure histogram, then you say, okay, so that's where you have infant mortality, and that's where you can
talk yourself into all kinds of things real quick.
Right, and it just doesn't work like that. You don't get that sort of those sort of characteristics. I mean, if you think, okay, there's a chance we'll have infant mortality, and there's a chance, obviously, then we'll have wear out for the residual products that you get through that phase. You'd expect to see essentially the sort of skateboard ramp at the histogram at the start, which would be relatively small, and then you'd see the then you'd see the histogram map out a shape based on your understanding of how that thing wears out. And if it's anything different, you go, hang on, I'm not going to even do anything until we get on top of that.
Right. But you're comparing it to what, knowing that you're dealing with bearings and in this kind of scenario, here's what I should see. And it gives you a point of comparison.
Exactly. But I always the reason why I always like emphasizing, think what do, try and predict what you expect to see. It hopefully eradicates some of that sort of confirmatory bias that we often have. But that's the data. They always do that first. I was doing sort of analysis for a car company. So here's the time to failure data in terms of days. And you go, okay, well, there's quite a few negative days here. What's going on?
Yep.
Oh, it must have failed before we sold it. Okay, cool. Yeah. Let's have a chat.
Let's figure out how that works.
Yeah.
I actually was in a legal case as expert witness looking at some analysis, and they were predicting negative 3 months time to failure on stuff. And I'm like, and you have to ask me why this is a problem? What's going on here? And it was they said, well, we're using Weibull++, and that's the answer we get. Well, then it got worse. Then they said, well, how do you pick, why are you using a different distribution for the exact same failure mechanism with each month's data set as it changes? He says, well, Weibull says that in their wizard predictor, that's the best fit. Okay, let's step back a bit here and think about what you're trying to do here. I'm going to put numbers in my calculator. It's going to give me an answer back and I file my taxes. Well, you might want to double check your calculations.
Right.
There's this one issue I have with the analysis is I agree with you, is guess, get a rational, think about it a little bit. What is it that this should look like, or what should it behave as? And the simple one is it should not be negative. This is time to failure information.
Good start.
It's a good start. But kind of, is this going to do it? I expect these to go for, one of my bosses said, well, what's your gut sense of this, right? We've been running this system for the last 5 years. We've had one failure. I think that was when a forklift ran into it. So if you're doing an analysis of it and you're getting all answers that it should all completely fail in 6 months, well, that just doesn't make sense because we've been running it for 5 years without problems. So you got to put a little bit of reality into your analysis. He called it the sniff test. This result doesn't smell right.
Yeah, and so I think there's a lot. There's no checklist. You go through. Okay, does the data have these characteristics? Is it all positive? Check. No worries. There's no checklist where you can go through and say, well, it's we didn't observe any of these characteristics, therefore the data's good. You got to use your brain. You got to think about how it could possibly fail, and say, okay, what should I expect to see if it fails in these particular ways? And to be honest, if you don't know what you expect to see, then you're not qualified to interrogate the data anyway. I mean,
that's where you go.
It's just shapes to you.
Yeah, that's where you go find the chemist if it's a chemical process. You go find the mechanical engineer, mechanical systems. You go find the experienced, and sure, anybody could drop a pile of data on your spreadsheet, and you could analyze it to any way you want and come up with all kinds of cool answers, but they all could be totally meaningless. You got to have a little bit of common sense or history or prior knowledge to go after it. But the other part, one is, have some idea what you should be getting and then look for those differences to check your work or check the input or check the analysis. Are you doing the right analysis? Those kinds of things. But I think also, I've created quick tools on Excel to, just play with simple equations that I just want to run the numbers through. I almost always then open up a textbook, knowing that they're not always perfect, but I open up one or two that I've used or I trust, or I open up a different software package and run the numbers through that. And is my coding giving me a rational answer versus what other people's solutions do for it? So I try to, and sometimes I'll even work it out by hand. If it's really important, I'll do as I hope I don't ever have to do it again, but a matrix inversion by hand. It's not something I look forward to, and I know there are people that do that just for fun, but not me. And but it's one of those things where it's you understand the data, understand that it's input correctly. What kind of things are you looking for out of this style of information or data, the set that you got picked up? But also check your calculations, check the programming, whether it's is this the appropriate model, and that's regression analysis, or is it did I punch in the wrong numbers? I've done that so many times, transposing numbers or inputting incorrect information, or calling the wrong column in an Excel and realize it later when it goes, that doesn't look right. So it's those kinds of questions, and I call it a healthy skepticism. Double check stuff.
Yeah, and I mean, a very specific example is how I do it. So I have my MATLAB code, which does Markov chain Monte Carlo simulation to get essentially as good an answer as it can possibly get, and call that MCMC for short. But a lot of people will say, well, MCMC is very prone to tuning. You've got to make sure the step size, this, that, and everything else. Otherwise, you won't get the right representation. And essentially, I leverage the fact that I don't think too many people do this. And when people talk about the pitfalls of MCMC, what if you've got, bimodal likelihood function for your parameters, and you go, it's actually impossible for that to happen in reliability. It's been proven several times. So the good thing is that when you're trying to characterize uncertainty in Weibull plots and things like that, there is this likelihood surface which is always going to have a peak around the most likely value. And I use my own sort of variation of slice sampling, where I actually create a video while MATLAB's doing its thing of its sampling and creating contour lines on the likelihood itself, or actually code it so that it numerically identifies its these contour lines, and you see all the samples, being randomly selected as you go. And I usually do that for the first 1,000, because when I often like doing up to 1 million data points, because why not? Sorry, 1 million samples, I should say, not data points, to really hone in the answer. But in the first 1,000, you can really tell if something is amiss visually, because our primitive human brains are visual more than anything else. Yep. And so I can actually replay the MP4, watch the contour lines of the likelihood function being created, which then, for those who have done slice sampling, allows me to perfectly calculate the slice dimensions for a particular likelihood, which means I'm not inadvertently excluding possible numbers, which leads to this thing called random walking, blah, blah, blah. So it's got a pretty robust approach that I always create an MP4 to show it being generated, and actually has a cool little sort of, like a drone, it circles around it.
I've seen that. It's pretty cool looking. But it's also one where you are building into your analysis a check step.
Right. You can see if something's amiss if you know what to look for. If the contour lines are over there and all the data points are creating another mountain over here, there you go. All right, what did I stuff up? Yep. And of course, because it's code that I use over and over again, constant debugging and continual improvement means that's getting less and less likely. Yep. But it's sort of the ultimate check step. But I always use the inbuilt MATLAB functions to estimate, for example, Weibull parameters, and compare that with what I get with my process. The maximum likelihood should be technically that should be the same number, but because you have to evaluate it numerically, there'll be some calculation errors, but they're within a micron of being wrong. But that's not the point. So that's how I do mine. I sort of have the first check is to compare it with the inbuilt functions, which have a few assumptions. But then I have my approach, which is I create a video to actually see what the computer's thinking. And if you know what to look for, you can get a really good sense of whether it's spot on the money or not. Yeah. You can't do that.
It goes back to the software package as a customer and as an analyst, is use a package that lets you get to the residuals. If you're doing a regression analysis, look at the differences from the model to your data. It's so informative in so many different ways. And there's some guidelines about what they should look like. And so this takes a little bit of effort to figure out what are the unusual patterns that indicate something's going on.
There you go. There's a flaw in your plan. It takes effort.
Oh, well, I'm sorry about that. It all takes effort. Otherwise, what are we doing? I can let the software just collect the data and plot it and go for, don't bother putting the actual data points anywhere.
Right. I mean, if you not interested in putting in effort, it means all you're interested in is getting a number.
That's easy.
That's what it means about you.
That's easy.
So it's you got to know, and I think one of the biggest issues is people get taught how to use software, but they don't get taught what that software is allegedly doing. And another good one is where you have a Weibull plot, and you say you got 30 data points, and of course the natural variation in those data points, it will have these sort of little 3 or 4 point runs, which look like little peaks or little troughs throughout the data. And you go, oh, okay, I've seen some people say, I can see 4 or 5 separate failure mechanisms because these little straight lines within this bigger set of 30 data points. You go, that's just not possible. That means you have failure mechanism 1 phasing in for 3% of the useful life of this thing, then it phases out. Then comes failure mechanism number 2, and it's just, if you don't know what to look for, you make boneheaded conclusions like that and put those in papers and present them at RAMs.
Well, the best one is somebody did a scatter plot of their data and says, well, this one looks like my uncle. I can see a face in there. I wonder what that means. We're really good at seeing faces.
I often put, for my Weibull courses, I often generate lines based on, for example, MATLAB or Excel generating random data based on a Weibull distribution. So there is no other random generator in there apart from a Weibull distribution. You put those data points in a Weibull plot, you say, okay, see, this is a straight line. And of course, it's with 30 or even 10 data points, it's going to be up and down and up and down. So no, that is what a straight line looks like.
Yep.
Well,
yeah, in my data analysis class in school, it was, well, how do we know if it's a straight line or not? And he says, plot it on an 8.5 by 11 sheet. I think he was Australian, so I think he used A4 sheet, and said, put a number 2 pencil over the top of it. And if it covers most of the data points, that's straight enough. It's very straight.
The other problem is that everyone thinks that, for example, in a Weibull plot and other plots, those data points are spot on. So if you have 10 times to failure, okay, you might use the median rank formula to get the plotting point for the first, second, third, fourth.
Yep.
Where does median rank come from? Median rank is actually the median of the beta distribution, which is used to model the likely place of the CDF for that particular data point. And so if you look at a Weibull plot, not only, especially the bottom left-hand corner, because you've got a logarithmic scale on the horizontal axis, and on the vertical axis, again, the scale for CDF gets really spaced out. You have all sorts of, let's call it noise, natural noise, not only from the fact that this is a random process, but that your CDF estimates are estimates, and they are less and less certain at the extreme edges. The most reliable CDF estimate you can get is the median, because if you've got 1,000 data points, you've got 500 data points above and 500 data points below, giving you a pretty good idea of where the separation is. But what happens if you're trying to estimate
the first percent, which is really fun to do,
and you have 20 data points?
Yeah,
it's the ability to project that low it gets really noisy really quickly. And if you don't know that the median rank formula is itself an approximation to the median of the hypothetical beta distribution, not many people even know that. And even if they do know it's a beta distribution value, so, well, it's actually an approximation. And the reason why is because the true equation is hideous. It's just, it's not cool. And so that's one thing probability plotting software can do better. They do come up with better CDF estimates because they're able to use better estimates of those beta distribution. And we haven't even talked about censored data yet,
Yep.
because the effect a censored data point has on the non-censored data points in terms of where the CDF is actually based on the line of best fit. So if you want to be serious about it, you're supposed to plot those data points, get a line of best fit. Okay, what does this imply for the censored data points? Reassess where those censored data points are likely going to be. Replot, keep going, replot, keep going.
Yep.
And if that sounds hideous, it's because it is. But that's technically what you're supposed to do. And if you're overwhelmed listening to this right now, you should be, which is why I use software like the coding I use. It just takes that all away once you've gone through the critical thinking to confirm that the Y-bill, the normal, or the bell curve, the log normal is the right curve for you. Okay, then let the computer deal with all those.
Well, at this point, if you never want to see another data set again, and you don't know where your calculator is, you turned off Excel and you're like, I'm looking scant-eyed at the mini tab. I'm like, that's part of it, is give it the due diligence to think through it and sort it out. And if this is just raising more questions for you, let us know. Head over to accendoreliability.com/go/SOR and get in touch with us. We're happy to help you become more skeptical of your data analysis.
Right.
And sometimes it's really as simple as just don't blindly trust whatever your numbers you're getting. There's a handful. Every circumstance is slightly different, but give it a good estimate, guess. Where should this be going? And look for those differences. And then in the analysis, give it some thought. What is this analysis actually doing? And is this appropriate? And how do I know? What kinds of things can you do to check it? But if you run into this kind of stuff for questions or want to improve your ability to analyze data, it's a way to go about doing it. And I think it served me well over the years. And Chris, sounds like it's driven you off the deep end of MATLAB. So, but let us know. Head over to accendoreliability.com/go/SOR. A couple ways to get in touch with us. Chris and I are available as the other hosts of the show via LinkedIn or our About pages. So, yeah, I think I'm going to go chop firewood the rest of the day. That's a lot more fun. Just kidding.
Fair enough. But, well, it's you just got to be comfortable thinking.
Yeah.
Critically, which means you might need to expand your skill set. But once you do, I think you start to realise how much can be saved and how much you could benefit your organisation when you understand how things are working, as opposed to trusting numbers from a computer.
Yeah, just turning the crank. Yeah. No, exactly. Right. I have to go figure out, did you use that video in a webinar?
I did.
Yeah, so we'll have to add that into it because it is way cool. It is pretty cool. All right. Well, thanks, Chris. I knew you'd have some thoughts on this one. We'll talk to you again soon. Take care.
Cheers, Fred. You too.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.